Have you ever been sitting at a red light, staring at that glowing circle of frustration, wondering, why now? Why does this light turn red exactly when you get there? And why does the cross street seem to get more green time even though no one's there? It's almost like the city has some secret system pulling invisible strings, deciding who moves and who waits. Well, you're not wrong, because every traffic light you pass, every green wave you hit, and every minute you waste waiting for red is all guided by a hidden algorithm, an unseen intelligence that quietly controls the flow of millions of vehicles every day. Before we dive deep into this invisible traffic brain, make sure you hit that like button and subscribe to the channel, because by the end of this video, you'll never look at a traffic light the same way again. All right, let's get into it. When you're at an intersection, what you see is a simple red, yellow, green signal. But behind that box of lights is a sophisticated system, a blend of hardware, sensors, and software, all designed to manage chaos. You might think it's random, but it's anything but. Traffic signals are powered by algorithms that balance human impatience, safety regulations, and the mathematical rhythm of city movement. The earliest traffic lights, back in the early 20th century, were manual. A police officer would literally stand in the middle of the street, switching signals by hand or pressing buttons. It was crude, slow, and often dangerous. But as cities grew and cars multiplied, it became impossible for humans to keep up. So engineers started designing machines to do it for them, automated controllers that could decide when to stop and when to go. Those first automated systems used fixed-time control, meaning lights changed at set intervals, whether or not cars were actually waiting. Imagine that, stopping at 2 a.m. for a red light on an empty road, all because some timer said so. Not exactly efficient, but back then it was revolutionary. As computers entered the scene, traffic lights got smarter. In the 1970s and 80s, engineers began to design actuated control systems, lights that could react to traffic instead of following a strict schedule. They used sensors buried under the pavement, called inductive loops, those metal coils that detect when a car is sitting above them. These loops send signals to a controller box that decides whether to extend the green light, cut it short, or switch directions. It might sound simple, but the logic behind those decisions is surprisingly complex. Every second, the controller runs through dozens of calculations, weighing how many cars are waiting, how long they've been there, whether pedestrians press the crosswalk button, and even how traffic is flowing in nearby intersections. It's like a conductor leading an orchestra, but instead of instruments, it's honking sedans and impatient cyclists. But that's just the beginning. The real magic happens when these lights start talking to each other. Modern cities are full of networked traffic systems. Instead of each light working in isolation, they communicate, sharing data through fiber optics or wireless links. This coordination allows engineers to create what's called a green wave. That's when multiple lights are synchronized so drivers moving at a certain speed can catch consecutive greens. It's why sometimes you'll cruise through 6 intersections without stopping, and other times you'll hit red after red because you missed the rhythm by a few seconds. Behind this coordination is a hidden web of math. Algorithms crunch through traffic counts, speed data, and even historical patterns to predict how cars move hour by hour. The goal? To reduce waiting times, improve fuel efficiency, and cut down on emissions, because idling cars waste more fuel than moving ones. But the deeper you go, the more fascinating it gets. Some cities have upgraded to what's known as adaptive signal control, a system that doesn't just follow a preset plan, but actually learns and adapts in real time. These systems rely on sensors, cameras, and sometimes radar to monitor traffic continuously. They detect congestion, identify accidents, and even adjust signals to let emergency vehicles pass. For example, imagine there's a sudden traffic jam because of a fender bender on one side of town. The adaptive algorithm senses the growing queue, calculates how to relieve it, and automatically tweaks the timing of nearby lights, lengthening the greens where needed, shortening them elsewhere, to keep things flowing. It's like a living organism, constantly self-correcting. One of the most famous systems like this is SCATS, the split-cycle offset optimization technique, developed in the UK. It constantly measures traffic in real time and makes micro adjustments every few seconds. Another is SCATS, the Sydney Coordinated Adaptive Traffic System, which does a similar job in cities across the world. Both systems can handle thousands of intersections, optimizing them on the fly. So what's inside the algorithm itself? At the heart of it, there's a set of mathematical models, typically optimization formulas, that aim to minimize delay or maximize throughput. They calculate how to distribute green time between competing flows, north-south, east-west, cars versus pedestrians, buses versus turning lanes. Each phase of the signal has parameters like minimum green time, maximum green time, and clearance intervals. The algorithm uses these to juggle priorities, but no algorithm is perfect. There's always a trade-off. If you give too much green time to one direction, the cross-traffic piles up. If you balance too evenly, everyone slows down. The art of traffic control lies in finding that sweet spot where movement feels natural, even though it's all mathematically choreographed. Some modern systems are now experimenting with AI-driven control, deep learning algorithms that don't just follow rules but discover patterns. They learn from millions of data points, GPS from cars, sensors, CCTV feeds, to predict where congestion will form before it happens. Think of it like a brain that's constantly learning how your city breathes. In Pittsburgh, researchers tested a system called Surtrac, an AI-driven traffic signal network that cut travel times by 25% and reduced idling by 40%. It worked by giving each intersection a kind of digital brain. Each light made its own local decisions, but also communicated with neighbors, sharing data about approaching vehicles. The result was a decentralized, self-organizing system, not unlike a colony of ants that somehow manages complex traffic flows without a central commander. And in the age of smart cities, things are only getting more connected. With the rise of Internet of Things IoT technology, traffic lights are being linked directly to vehicles. Imagine your car sending a message to the light ahead saying, "I'm coming at 45 kilometers per hour," and the light responding, "Got it? I'll stay green for 3 more seconds." That's the dream of vehicle-to-infrastructure communication, or V2I. It could make traffic smoother, safer, and far more predictable. Even more futuristic are AI-powered simulations that train algorithms in virtual cities before deploying them in real ones. These digital twins of urban areas allow traffic engineers to test different signal plans under thousands of conditions, rush hour, rain, sports events, without touching a real light. It's traffic control meets video game simulation. But here's something most people don't realize. These algorithms don't just manage cars. They also balance politics, budgets, and public pressure. A single change in timing at a busy intersection can spark complaints, accidents, or applause. City engineers have to fine-tune the system constantly, collecting feedback, studying crash data, and updating algorithms based on ever-changing driving habits. And with the growing popularity of electric scooters, bicycles, and autonomous vehicles, the complexity keeps rising. How do you time a light when half your traffic moves at 60 miles per hour and the other half pedals at 10? How do you prioritize an ambulance when it's competing with a self-driving car that's following the rules perfectly? These are the questions that traffic algorithms of the future will need to answer. But for now, every time you stop at a light, remember that it's not random. A silent conversation is happening beneath your tires, between sensors, servers, and circuits, deciding who moves next. Somewhere, a tiny piece of code is calculating fairness, safety, and efficiency in real time. It might not always feel fair when you're stuck at red, but it's part of an intricate dance that keeps cities from collapsing into gridlock. Next time you glide through a series of greens, know that you're surfing on the rhythm of mathematics, the pulse of an invisible system that never sleeps. So the next time you're tempted to curse that red light, think of the unseen algorithm that's quietly doing its best to keep everyone, you included, moving safely and smoothly through the city. And who knows? Maybe one day, with the rise of autonomous vehicles and fully connected roads, traffic lights themselves might become obsolete, replaced by a seamless AI-coordinated flow where no one ever has to stop again. Wouldn't that be something? Thanks for watching, everyone. If you enjoyed learning about the hidden world behind those everyday red, yellow, and green signals, make sure to hit that like button, subscribe for more fascinating deep dives, and share this video with someone who's always complaining about traffic.